All right, I'm going to use green because it's not very scary. Okay, assume Gedanken conditions exist in this example. All right, so it's a thought experiment. This could never actually happen. A stationary observer on Earth sees a very fast car passing by, travelling at 2.5 times 10 to the power of 8 meters per second. In the car is a clock on which the stationary observer sees 3 seconds pass. Calculate how many seconds pass by on the stationary observer's clock during this observation. Use the speed of light as 3 times 10 to the 8 meters per second. All right, so what we have a very fast car. Hope you're not laughing at my car. This is a work of art. All right, there is a very fast car, sorry. There is a person down here who is stationary. That is travelling at 2.5 times 10 to the 8 meters a second, and this person has a watch. Okay, the car has a clock. And so, our stationary observer sees 3 seconds pass on the clock that's in the car. We want to know how many seconds pass on our stationary observer's watch. All right, so first things first, let's not worry about T and T0 for a moment. Let's just get our Lorentz factor. So, our Lorentz factor is equal to 1 over the square root 1 minus v squared on c squared, which is equal to 1 over the square root 1 minus, what's v? 2.5 times 10 to the 8?
Yes.
All squared on 3 times 10 to the 8. All squared. Okay.
It's a big number.
Is it?
No, it's a bit small.
Tell me what you work out when you pop that into your calculator. I want to know what you get for your Lorentz factor. Someone call it out. The longer you take to call something out, the longer this period of silence on our video is going to go.
1.8.
1.8? I don't mind 1.8. All right. So, Maxim's saying 1.8. Anyone disagree? Anyone agree?
So what units though?
It's not units. No units for it because it's a ratio of speeds. Yeah, Lorentz factor has no units. So, if we've got 1.8, if you have a look at the previous slide where it shows us our Lorentz factors, you'll see that it gives you a Lorentz factor when we are travelling at 2.6 times 10 to the 8, gives us a Lorentz factor of 2. So if we're travelling a little bit slower than that, we would expect a Lorentz factor of a little bit under 2. So 1.8 works for me. I'm going to assume that's right. Okay, so the next thing then is our time dilation equation. T equals T0 lambda. Now, remember, T0 is the time measured in the same frame of reference as the event occurring. What is the event in this case? The clock on the car. The clock on the car is the event. So T0 is the time in that same frame of reference. And so, yeah, it is 3 seconds. We are seeing 3 seconds pass on the clock's dashboard. That is our T0 value. Okay, T0 is the time measured in the same frame of reference as the event. So, if our T0 value is 3, and our Lorentz factor is 1.8, what does that come out to? 5 point something?
5.4.
5.4. So our observer would see 5.4 seconds pass on their watch while it takes 3 seconds to pass on the clock's dashboard. Okay? Remember, the hardest part about this, if you're good with putting the Lorentz factor into your calculator, and I strongly recommend you practice that. If you didn't get 1.8 here, let me know why. Let me know and I'll come and help you. But the hardest part about this is identifying which is t and which is t naught. T naught is the time taken for the event in the same frame of reference as the event.